Hello, everyone, and welcome to the second week of office hours for Intro to ABM. Just kind of waiting for people to come online, but we're now live. So yeah, I'll send the links out again so that everyone knows where we are. Come on in and join whenever you can, so that we can talk about what's been going on this week. As you all know, this week has been more about finishing up Unit 1 than it has been about starting any new material. So we're just kind of rolling through that. The exam for Unit 1 will be finished, will be available at the end of this week, so you can go ahead and take that. Yeah. We have a couple of people who I think are going to join us. I see a couple logging in right now, so we'll get to them in just a second. Just like I said, I'm posting the link for everyone, and we will get to that in a second. Okay, just send it out on there, and I will send it out on the forums too as well, real quick. So we have it all up and running. Okay. Okay. So yeah, so just a couple quick announcements. First of all, as I mentioned, this week is mainly about finishing up the material that's in week 1. New material for week 2 will be available starting next week, at the beginning of the week. And that unit, so this unit, as you know, is all about what agent-based modeling is, why you want to use it, what you might use it for, what advantages it has over other methodologies, what disadvantages or trade-offs it has with those other methodologies. Unit 2 is really getting you into starting to use NetLogo and agent-based modeling, so that we'll really start to try and understand that. And that's really where the focus is for that unit. One question that came up in the forums is trying to post some references to the materials that we talk about during the discussions, and I will definitely try and make those available. Anna Maria, actually, the TA for the course, will be putting some of those resources up and online as she gets to them. Another question that came up in the forums earlier this week was what chapters in the textbook, Introduction to Agent-Based Modeling, correspond to what units in the course. And essentially, yeah, that's a great question. And from now on, I'll try to mention at the beginning of each week's lectures which chapters they roughly correspond to. It's pretty simple, actually. So Unit 1 is roughly chapters 0 and 1. Unit 2 will be roughly chapter 2, and so forth. So they actually match up almost exactly number for number, because we didn't start with Unit 0. So that's probably the easiest way to see the relationships. And yeah, so as I mentioned, for those of you who are listening, if you want, you can send in questions through the Q&A app on Google Hangouts. You can also try and tweet at me. I'll do my best to kind of notice that as we're going through. And I did have a couple of ones set in ahead of time as well. It's a little hard during the live hangout for me to check email, but if you have a Twitter question or if you post it for your Q&A, that's a good way to do it. And again, if you ever want to join in on the hangout ahead of time, feel free to send me your email at roughly at least usually a day ahead of time, and then I can invite you in. And yeah, so that's basically the way it's going to work. So I see we do have one viewer, or one of the invited members is online. So it looks like John Villarga is online. John, are you there?
Yes.
Yeah. Okay, great. Did you have a question you want to talk about, or are you just interested in what's going on?
I have some questions, but it's not, I don't know if it's like right for the course, because I'm actually working on agent-based modeling, but using Python.
Okay.
So I was just wondering if you have if there is probably any correlation between NetLogo and Python. because I know that NetLogo is more like an agent-oriented programming language, but
Mhm.
in Python, I will have to actually build each agent like by using classes.
Right, right. Great question. So, as I mentioned, I think in one of the video lectures, I meant to mention, at least if I didn't, was that there's obviously at least a couple of different ways to build an agent-based model. One is kind of the way, kind of the traditional way to do it was the way that you actually are doing it, right? Which is to kind of what we call roll your own, right? Which is basically build your own classes, integrate them within the agent-based modeling concepts and framework, and then construct it all yourself. Um, there's a lot of benefit to that in that you get complete control over the model, right? Like you know exactly how it's working, how the agents are working, and you can be as efficient as possible. Makes it fairly easy to integrate. I personally, even though I've written agent-based models in, I've written them in, I don't know if I've ever done it in Python because Python's a fairly new language in my world, but I've written them in C and Java and a couple of other languages in the past, and I still write most of mine in NetLogo primarily because of the fact it gives you the freedom of having those classes available already. I think, if I remember correctly, I believe there are some packages out there for Python that help you kind of build agent-based models. The one I probably heard about the most, I don't know, I haven't actually played around with them, I just have heard about them, is one called Mesa, which is an agent-based modeling framework in Python, essentially. So that's another hybrid option that you might have, right, would be to use a package that someone else has built in Python. I don't believe. So how can I put this? NetLogo has two things that we'll talk about throughout later on in the class in more detail. But it has a controlling API, which is an API that allows you to control to have a NetLogo be controlled platform, right? But then it also has what's called an extensions API, which allows NetLogo to allows you to write your own commands in NetLogo to control another language. So you, for instance, could build Java wrappers around Python componentry that you had before, then call them directly from NetLogo, or you could actually call NetLogo via some Java wrappers from Python. It's difficult to do, but it's possible. So there are ways to integrate. Is there a specific way you're planning to integrate them, John, or a specific way you're planning to look at them together?
What do you mean? For the agent-based model?
Yeah.
Or you mean to connect like NetLogo with Python?
Yeah. Oh, were you planning to connect them, or are you planning just?
No, I'm not. It's just
Okay.
that for my research, my PI wants me to use Python.
Okay.
And yes, I've been using Mesa, but it's a new library, so it's still very limited in terms
Yeah.
of the spaces that it has. I can probably use. It only has the grid, the multi-grid,
Mm-hmm.
and for example, for my project, I need like something more robust. You know what I'm saying?
Right.
Like I want to try different spaces so I can probably build the best model.
Okay. Yeah. I mean, so to that extent, what I would say is just we're gonna talk about. So this course and the textbook as well actually are not NetLogo textbooks, right? And it's not a NetLogo course, right? It's really about teaching you how to do agent-based modeling using NetLogo as the example language, right?
Okay.
And the reason why we decided to do that was because of the fact that, even if let's imagine we were to write a textbook or teach a course that had no language whatsoever, right? We would still have to have some sort of pseudocode to help you understand the applications and the software and the particular examples, right? And so to that extent, we chose NetLogo. But what I'm trying to emphasize here is that I think you'll still get a lot of value out of the course, even if you're going to write your code in NetLogo in the end, or sorry, in Python in the end, right?
I'm actually what I'm planning on doing now is by trying to build like a model in Python, NetLogo, probably compare them to see if they give the same like emergent pattern, something like that.
Yeah, that's actually a fantastic idea. I actually, and we'll talk about this. I think it's in Unit 7. But I'm a firm believer in what's called replication, right? Where you basically try and take a model, even if you've written the model yourself, and build it again in another language. I did that with actually one of the earliest models I built both in Swarm and in Objective C, or sorry, in Swarm in Objective C, and in Repast in Java, right? And it was interesting because it kind of teaches you what are the differences, what are the kind of the assumptions you're making with the two different languages. I highly recommend going down that path. That's a great idea for sure. And so yeah, and I think a lot of times I often recommend that when you start a new model, there's this. There's this old writing adage, I can't remember who it says right now, but which is destroy your pretty ones, right? Which basically means, throw away what you did in the past and start anew based upon what you've learned, right? And so the idea is, build it in NetLogo. Then if you want to do the final version in Python, right, you've kind of learned a lot from building the version in NetLogo. I think that's a great way to do it. Or, do them at the same time and compare and contrast and see what the differences are.
Okay, thank you.
Okay. Great. So we got a couple other people who have joined us. It looks like Sebastian and Paula have joined us again, and Alberto Katica has joined us as well. So hi, guys, for sure.
Hi.
Hi. Alberto, do you have a question? Did you want to talk about something?
Many questions indeed. Nothing specific. I mean, you're still in the early stages of the course, and it's actually not the very first exposure I've had to agent-based modeling.
Okay.
So I'm looking forward to getting deeper into that. I was kind of listening to your conversation with John and the choice of programming tool when you're doing modeling. Right. I think everybody's there, has to make that choice at some point in time. And so far, probably more like John, I've been building my own stuff because I'm a network guy like you, I guess, even though I don't know you very well yet. And I do my own stuff in Python plus Tulip.
Okay.
Which is really cool because of a fast prototyping capacity. But the thing is that that's better to give you a sort of overall idea of big picture of how the system works. Whereas I'm quite fascinated by what you showed, I think, in one of the very first lectures, the traffic model.
Right.
So the idea there is what the system does is actually represented by what a single agent does in the system, the red car. So I guess NetLogo is better at doing that. In fact, after your lecture, I tried to code this into Tulip, and it's kind of on and off. I mean, of course you can do it, but it's really not. The main issue is when I do the final layer of analysis, I go out of Python. Maybe I shouldn't. And I go over to Stata because one of the people I'm working with is a big fan of Stata and a super master Zen Ninja user of Stata. So I use Stata, but Stata is really, really bad at that stuff. So I end up with anyway. It's a really interesting approach, like targeting a single user. And I was wondering, do you have a way to check that your single user is actually, like, the red car is actually representative of every other car in the model?
Well, yeah, that's a great question. Yeah, so I do think that. So first of all, let me unpack a little bit of what you're saying, right? So I do think that one of the powers of NetLogo. It's also true of some of the other agent-based specific platforms, right? So Repass, for instance, and some of the other ones also, is that you have this control over individual elements within the overall agent system, right? And the fact that you can play it out in real time, looking at the actual agents and observing exactly what they're doing. So yeah, great point. I think that that's something I probably didn't talk about as much as I should have, which is that the red car is this great example of how looking at aggregate statistics of the model isn't that interesting, right, in some cases, because it's actually the individual behavior that's interesting. Now, trying to determine if the individual car is representative. So I think what you would want to do, that's a great question. One, I don't know if I've ever had asked in exactly that way. I think one of the things that you might do is if there's a particular behavior. So for instance, in the traffic model, right, the behavior of the red car that you're really interested in is the fact that it speeds up and slows down, kind of like this constantly, right? And it's constantly going up and down. So one thing you could do would be, and this is something I have done, is we do plots where we look at the behavior of every single individual, right, simultaneously, and see if the behavior of every individual kind of corresponds roughly to what we're seeing from that one individual, right? So you could imagine instead of just drawing that red car's behavior, you had the speed of every single car on it. Now, at some point that becomes hard to read, right, because of the fact that you might have some of them speeding up and slowing down at the same time. So you may have to do some time shifting to get the plots to look kind of the right way and things like that. It can be difficult to do. But once you've identified a particular behavior of interest, right? So in this case, right, the behavior is that it never maintains the same speed for very long, right? It's constantly changing speeds. Then once you've done that, you can usually determine a measure of interest, right? So maybe how long it remains at any particular speed, and then measure that across all of the cars, right? And see if all of the cars have roughly that same phenomenon. But this is not a mean, right? It's not like you're not taking the average, right? Instead, you're noticing the behavior of one individual, and then you're seeing if all the other agents have roughly the same behavior or same exhibit. Does that make sense, Bert?
It does, but can I follow up, or am I taking too much time?
Go ahead.
Okay, so at one point, you're going to need to have some kind of statistical indicator of agent behavior. Right. So suppose you're looking at something like a life cycle. Like, for example, now I would be interested in figuring out simulating life cycle of users in an online community. And that as a network, it can be modeled as a network phenomenon. Mm-hmm. And suppose a typical life cycle would look like, well, you join, and then you'd be fairly active initially, and then you would lose interest and you would drop out. Mm-hmm. And you can tell if this is the case for any particular user because you'd have a curve that goes up and down in terms of activity over versus time. Mm-hmm. But it's not very clear to me how I should statistically test for it, mm-hmm. right? Because if you cast your network too wide, it will be up, down, life, death, right? That's always true. But if you cast it too narrow, it's not clear what you're measuring because at any given point in time, of course, people are doing different things. So you could normalize and say, let's imagine that everybody starts at the same point, like the zero. My joining date will maybe to coincide with your joining date, and then we can track both our graphs or something like that. But at the end of the day, how do you test the hypothesis that my cycle is the same as your cycle? Mm-hmm. What you do?
Yeah, I think that's a very difficult question. I think it's hard to answer in kind of the general context, right? That's for sure. I should mention, right? So like let's talk about how you approach this problem a little bit in more detail, right? So the problem we're talking about is essentially I have a bunch of agents. They're all doing something, right? And I want to find out if the way I'm capturing their behavior, the statistical description that I'm using to capture their behavior, is actually descriptive of the agents, right? And then further, I want to test, once I have an idea as to what that behavior is, I want to test to see if all the agents follow that pattern of behavior, right, through some sort of statistical test, right? It's essentially kind of like taking your question, I'm trying to take it to a higher level a little bit, right, a more abstract level. And so really what you start with, right, is you start with your model. You've built your model up, it's running, right? You then, one of the things that the red car example from the traffic model shows us is that it's helpful a lot of times to visualize the behavior of the agents so that you can understand and start to come to grips with patterns of behavior that are not really well described by traditional means you might do that behavior. So now I've done that. I've gone through and I've noticed a pattern of behavior. In your case, it's this life cycle behavior, right, that I have for the individual. And I want to ask, how similar is that life cycle behavior to the behavior of any other individual in the model that I'm looking at, right? So yeah, so I hate so at that point, right, once you have that notion that I want to try and figure this out, you have to go back to statistics, right? You can't use visualization as well anymore because of the fact that now you have to compare one pattern to many, 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 many other patterns, right? And so you have to ask, how different are those patterns from each other? Okay. So now I hate to say this, but I think that the answer is that there is no single answer, right? That you can't, there is not one statistical test. It really depends upon the particular pattern of behavior that you're interested in looking at, right? And so, you can do things that we'll talk about later on in the analysis section, like maximum likelihood methods, for instance, right? Which basically say, given a particular model, what's the probability that this pattern of behavior that I'm observing was generated by something like that model? In this case, I don't mean a computational model, I mean a statistical model, right? And so doing things like that might be your answer, but it really, really depends upon what kind of data you have. Do you have time series data? Do you have point data? Do you have network-based data, right? And for each of those, you're going to have to come up with, there's actually a different suite of tools that you might want to use. And in some cases, you actually have to design your own tools to answer that question. So it's really about, essentially what you want to do is you want to create an ideal description of the behavior that you're thinking that all the agents are exhibiting. And then you want to test by looking at some sort of confidence intervals around that ideal description, how likely it is that any of the other behaviors are probabilistically similar to that behavior. Does that? I know that doesn't help. That's not a very satisfying answer. Maybe we'll get to some more satisfying answers as we go on through the course, but I don't want to jump way ahead at this point. Right?
Absolutely. I guess I was not looking for a silver bullet. I imagine there are examples, so people that have had to do this in the past, and they came up with a library of methods, and then you can take this closest one to whatever it is you're doing and hack it so that it fits your particular needs. The case of a red car is actually pretty interesting, because you're going to see, if you take any car, you're going to see cars that go slower and then faster. But is there really a traffic jam? As you were going through the lecture, I'm like, you said the result is a traffic jam, and I'm like, wow, that is really an eye of the beholder phenomenon, because when you do statistics does not see the aggregate, right? It thinks in terms of representative single agent, so it can't see the traffic jam. It can only see slow cars.
Right.
And then what a traffic jam is a low probability, very low probability of fast cars. Right. So you have to make a test that will describe a collective phenomenon in terms of a representative agent, because that's the game of statistics. It's really not. It has an easy interface with the complexity science that you guys are doing. I think.
Yeah. Yeah, I very much agree, right? So you're right, right? The statistics in terms of the traditional approaches to statistics, using means, using averages, things like that, would not give you a very good description of a traffic jam, right? Actually, it's interesting. I like your characterization of a traffic jam, right, as a low probability of a fast-moving car, right? Because, in fact, I actually characterized it slightly differently in the lecture, if you go back, which is that I characterized it as the fact that you don't maintain the same speed for any length of time, right? That you're constantly varying your speeds because of the fact that you're going fast and then you stop, and then you go fast and then you stop, as opposed to a free flow state, right? Which is one where you're basically maintaining the same speed constantly over time. So one way to actually use traditional statistical methods to describe my characterization of the traffic jam would be to look at something like the variance of the speeds of all the cars over time, and they'd be much higher in cases in which traffic jams had occurred than in cases in which they hadn't. But interestingly enough, right, in both cases, in both my description and your description, right, um, you would have to know what the world looked like without a traffic jam, right? Because otherwise, you're not really, because you're measuring these things relative to other things, right? You're measuring them relative to the world of fast-moving cars, or relative to the world of traffic jams or non-traffic jams, right? So, yeah, interesting, great question, Alberto. That's for sure. So I also see Sebastian and Paula are there. Do you have any questions this week?
Yeah, we have a question related to the segregation model.
Okay.
Yeah, in the segregation model, there's something like a tipping point where the borders are not stable anymore.
Mm-hmm.
I mean, in general, the model is very robust,
Mm-hmm.
but after that point, the borders never reach the stability.
Mm-hmm.
Uh, will that be considered chaotic? Chaotic?
Um, so, so chaos has a very specific set of meanings that is not really what we're planning to go into in this course. So I don't I'd have to look back. I don't believe that those borders would match that point would match all the definitions of chaos, right? Um, One thing in particular is true is that we talk about later on in the course, right? Is that one of the precursors of chaos, one of the defining characteristics of chaos, is that points that are initial conditions that are approximately the same don't result in approximately the same outcomes, right? And I don't think that's true in the segregation model. Like if you can move one or two individuals within the model and get roughly the same outcomes, right? Whereas in a truly chaotic system, that would not be the case, right? Now, that being said, there are ways, if you play around with the parameters of the segregation model, to create systems that are very complex or that enter very interesting patterns of behavior that are almost chaotic in appearance, right? But I don't think that they meet the formal definition of chaos, no.
So the segregation model features self-organization, which is like a characteristic of complex systems. It
Mhm.
doesn't features the uh, chaotic or the all the feedback that makes chaos. Uh, so you can have complex systems that are very chaotic, but other complex systems that are just self-organized and very stable, right?
Yeah, that's a great way to describe it. I think that's an excellent description. Yeah, and we hadn't really talked about self-organization too much in the class yet, right? And in fact, it's a great point. I should probably add that in for unfortunately for next year to the key terms lecture, right? Talk specifically about self-organization. Let me put a note for myself on that, right? But yeah, so for those of you who don't know. Self-organization, and I think actually Cosma Shalizi and colleagues have a great paper that kind of defines self-organization for me really well, which is that a self-organized system is any system where the complexity of the system increases over time without external inputs, right? And so, the system becomes more organized in some respects without having somebody force it to be organized, right? So it's self-organized, right, is the description. And Cosma actually describes that very formally by looking at the entropy of the system and how predictive it is, and then describing about how if the entropy of the system decreases, then you have a self-organized system, right, which makes sense, right? So you can think of many things as self-organized, like life, for instance, right, as being self-organized. We go from a lot of entropic states to less entropic states that are more predictable. So, anyways, just a quick note for people who don't know what the word self-organized means, right? Yes, I think that's true. I think very much you can have complex systems that are self-organized but not chaotic, and you can have complex systems that are both chaotic and self-organized, right? For instance, pair box sandpile model, which hopefully we'll talk about at some point during the course, essentially can be done as an agent-based model, and it exhibits chaotic features, and it self-organizes as well, right? The segregation model, I don't think, I've never seen someone actually do a full explanation of it from a chaos theory standpoint, but I don't think it qualifies as being fully chaotic. However, it does qualify as being self-organized. Yes, that is the case. Do you guys have another question, or Sebastian and Paula?
Yeah, I have another question. So, how do you can determine if the system is chaotic or just random?
How do you determine if the system is chaotic or just random? That's actually a great question, and I feel like I should actually punt on this one a little bit because we have an entire other MOOC available at Complexity Explorer on this topic, and if you go to, I believe it's I'm trying to pull it up real quickly here. Let me see, I can actually do a screen share and do this, right? So, what the heck? Why are you not showing this one? Okay, there it is. Okay. So if you notice, there's a course that started on July 5th called Introduction to Dynamical Systems and Chaos, right? So if you're interested in those kind of questions, oh, here, I didn't actually share that correctly. Oh, that's not the way I wanted to share. Stop that. Let's see. Okay. So there's a course called Introduction to Dynamical Systems and Chaos being taught by David Feldman. I highly recommend going to check that course out. The truth of the matter is that it can be very difficult to tell the difference between systems that are purely chaotic and systems that are random from an external observation, right? A lot of times you have to look at that by actually knowing how the system actually behaves in many of these conditions and trying to build a model that describes those systems, right? So to that extent, it's a hard question to answer, but I think it's a very interesting question to answer. And it can be very valuable to know the difference between chaotic systems and completely random systems, because chaotic systems, despite their name, do have some ability to make very, very rough predictions about them, right? Like you can't really predict where they're going to wind up, but you can predict where they're not going to wind up in many cases, and that can be as valuable as knowing where they're going to wind up in certain conditions, right? So I highly recommend checking out David's course if you're interested in that topic. and he can kind of explain that in more details to you. As I said, we probably won't get into chaos in too much detail in this class, just because there's a whole nother class already being taught on that subject. Any other questions out there?
Do you mind if I send you an email about some like questions that I have? It's not directly related to the course, but it's more about a class in my school that is like about agent-based modeling. So I just have a few questions that I wonder if you can probably answer them.
Yeah, sure. I'm happy. Feel free to send me any emails along those lines. As I said, you can send them to ABM at Complexity Explorer. That's the one I monitor, right? And actually, I don't have an official email for myself right now because I am starting. I was at the University of Maryland, but starting at NC State University actually today, and so I don't have that email set up. So as soon as I get that set up, I will let you guys know that email address as well. But ABM at complexityexplorer.org will work fine in the transition. Okay?
Okay, thank you.
Yeah, great. So I do have a couple of questions from the audience that got mailed in ahead of time, so I'll take a little bit of time to answer those. And if any of the live participants have questions in the meantime, let me know. And I always like to check if any of you who are viewing want to tweet at it, that's fine. Or if, and I'm looking real quick, scanning the tweets, doesn't seem like anything's coming recently. Or you can also ask via the Q&A app on the Google Hangouts, and that'll work as well. Okay. So the questions I had mailed in. So one is from Min Lai, and Min Lai, and they say the question is, could you describe the analysis process that goes on after you've built and run a model? What are some of the parameters that describe ABMs in terms of, say, complexity or emergence? And also, how do you determine them? Do you implement statistical techniques, and has the development of machine learning been leveraged to better describe the parameter space of these models? So this is a great question. Actually, this is somewhat related to the discussion that Alberto and I were having earlier, right, about how you actually look at and analyze these models, right? I would say that besides teaching agent-based modeling and computational modeling, I also teach data science at the university. And one of the things I always teach when you're looking at data is to start off right off the bat by just visualizing the data, right? And so that's what I recommend doing with the agent-based models as well as the first step of kind of analyzing the results. It's just visualizing the results. And for ABMs, a lot of times for that, because of their path-dependent nature in a lot of cases, and because of some of the tipping points and other phenomenon you see, I often like to visualize all the results and not do any means or averages or anything right off the bat. And that kind of gives me a first idea of the patterns of behavior that I'm examining, right? Now, the parameter spaces are quite large, right? And so, it can be difficult to look at all of those, right? But, I try and do my best to try and kind of get a good idea of how the inputs I'm interested in affect the outputs I'm interested in, right? And I do that primarily initially through visualization, and then I come up with maybe some specific statistical tests or some specific graphs. I tend to often think about these questions in terms of what do I need, what I call deliverables, essentially. I'm originally an engineer. That's the way I was trained, right? And so I tend to think of, if I want to use this model to convince somebody of something, what are the deliverables that I would have to use to convince them, right? What are the things I would have to present to them? So once I've done a visualization and convinced myself of the story, I then think of the graphs or the tables that I would have to present to them, right? So what are some of the parameters that describe ABMs in terms of, say, complexity or emergence? We just had a little bit of a discussion about self-organization. That's a kind of an emergent phenomenon that you often observe. And one thing that's been used successfully there in the past, in a lot of models, is measuring the entropy of the system, measuring how predictive the system becomes over time, right? How well it describes future states. So that's one particular measure that's often been used. I don't know if there are other measures that I would say are specific to agent-based models. There are a lot of measures out there that are kind of just standard measures that you might use in other contexts. One thing that I often like to do, just to kind of explore the relationship between, say, a set of inputs and an output within the model, is just use standard statistical techniques like regression, right? So I create a bunch of model results with a whole bunch of different input parameters, and then I just regress my output parameters on my input parameters to see which of the input parameters are actually having a major effect on my result. And what's nice about that from an agent-based modeling standpoint is that a lot of times when we build these models, we're not actually sure, because of all the interactions, which of the input parameters are going to have a large effect on the output, right? And using something like regression helps you kind of take a first pass at looking at some of those things. How do you determine the parameters? Well, that's tough, and so we'll definitely get into this around Unit 7 in the class, where we talk about validation of the model. And determining input parameters is what we call making sure that the model has empirically valid inputs, right? I highly recommend, whenever possible, trying to think about, rather than think about an abstract model completely, even though your model is an abstraction of reality, thinking about a concrete thing like a day's worth of time or a year's worth of time, and then trying to think about parameters that might be reasonable within that space. And it's not entirely important that your parameters exactly match real-world data, as long as the relative scales of the parameters match real-world data. So, for instance, if I have a parameter in, so a standard model that we won't probably be building in this class, but that Uri talked about, is the wolf-sheep model, right? And in that case, you know, you have all these parameters to control how fast the grass grows and how many wolves there are and how many sheep there are. It's not important that you model exactly the real biome of having the right number of wolves and then the right number of sheep. But as long as you have relatively the right ratio of wolves to sheep, you can get a pretty good model and a pretty good understanding of what's going on. Finally, do you implement statistical techniques? Has development machine learning been leveraged there to describe? Right. So yeah, so I already mentioned I do implement statistical techniques in many cases. And yes, sorry, there's a little bit of noise in the background here. I often do use machine learning techniques nowadays to emphasize what's going on. In fact, we will definitely talk about in Unit 6 a tool that one of Uri and I's former students developed, who's now a professor himself, Forrest Stonedahl. He did some great work on a package called behavior search. And behavior search is essentially using machine learning to search over your parameter space such that you find outcomes you're interested in. So let's say I have a model, and that model produces output, and I want to see how well that output matches real-world data, right? I can write a function that describes how different that model's output is from the real-world data, and then I can use machine learning, and in the case of Forrest's package, genetic algorithms, a lot of times, to optimize the parameter space so it best matches the real-world data, right? And that's kind of an interesting way to think about how to explore these spaces. And that was actually originally proposed by John Miller, who is a Santa Fe professor who's done, and also at Carnegie Mellon, who's done some great work in computational social science. Yeah. And so, and he called it active nonlinear testing, the same idea as behavior search in many respects, right? But yeah, so machine learning definitely has been leveraged in many cases to better describe the parameter spaces of these models. Cool, great question, Ming. So, thank you very much for those questions. Had one other question that was sent in from Daniel Espina Medina. He says that Uriel Linsky talked about emergent phenomena as organized patterns that emerge from the interaction of distributed agents. I am familiar with this definition, but I started to reflect what are the meaning of organized pattern order. What constitutes an organized pattern? While the flocking birds we saw in the first phase appear to us as clearly organized, and we are capable of detecting and even predicting cycles of other paradigmatic examples of complex systems, such as ecosystems, it is less clear that a financial system, much less all the other interlinked markets of an economy, could be described as an exhibiting organized patterns, and yet it is clear the dynamics of markets are emergent phenomenon. So my question is, in what sense do these type of messy systems, often social or economic, which have less obviously regular dynamics, can also be considered to exhibit order and organized patterns? And a possible follow-up question, can ABM be used to understand the why and how of the lack of regularity in certain complex systems? So that's a great question, right? And this is actually, I think this is also a little bit related to the conversation Alberto and I were having about how do you figure out that a pattern of behavior is regular or organized. And I think that the answer is, well, let's think about what it means to be regular or organized, right? And what it means to be regular or organized is simply that it's a recurring pattern that is in some ways predictable. It's something that you can say will occur again and again, right? So like the flock of birds, we see it over time and constantly, right? To that extent, I think that we can say often that social and economic systems, messy systems, they may have less obvious regular dynamics, but they can be considered to exhibit order and organized patterns, right? So, for instance, the boom and bust cycle of the classic stock market scenarios, right, is something that's a fairly, to some extent, pattern that you can observe, right? Now, the exact nature of that pattern, much like the exact nature of the flocks, is not necessarily predictable, right? Given a flock of actual wild birds flying around, I may not be able to predict where they're going to be next, right? But I know that they're going to form a flock-like structure, right? And in the same way, I may not be able to predict when the next bust of the economic cycle is going to occur, but I do know that there's probably going to be one at some point in the future, right? And so, in fact, being a social scientist, I'm in many ways more interested in using agent-based modeling to understand these quote-unquote messy systems than I am in understanding the natural systems that exist, right? I do think there is kind of a question that Daniel's asking that's a little interesting. There's a lot of people who try to define emergence as something that surprises you, right? And I have a problem with that definition because it seems to mean that means that once we understand everything, it is no longer emergent, right? Because it no longer surprises us, right? Once we know the rules of behavior that generate the flocks, right? If you talk about emergence or organized behavior as a surprise, right, then it's no longer an emergent pattern. The flock is no longer an emergent pattern if you define it that way. So as we mentioned, and as both Uri and I think, defined it, right, we define emergence as the interaction of many individuals giving rise to organized patterns of behavior, right? Especially when those patterns of behavior are not what we sometimes call entailed at the level of the individual. In other words, the bird doesn't know what a flock is, right? The individual stock trader might know what a boom in the stock market looks like, but he can't create one on his own, probably, or she, right, for that matter. So I think that's very important to make a definition that these are not things that are necessarily surprising. They're things that are just the results of a bunch of individuals acting together. So Daniel's final question was, can ABM be used to understand why and how the lack of regularity exists in certain complex systems? Yeah, I definitely think that's the case. I think it's you do often, so the way you often see this is you see people who build models that explore regularity, and then they look at where parameter ranges where that regularity breaks down, right? So for instance, if you go to the segregation model, right, you can actually cause that model to fail by doing things like increasing the density of the world to the point where there's almost no free space. If you do that, the system just never settles down, right? It's constantly changing, right? And so there are certain spaces where you can explore the lack of regularity in the system, right? And essentially the segregation model would imply that if densities of living are too high, no one is ever happy, right? And that no one ever kind of settles down, which makes sense, right? And so you could explore that in other cases. You could look at cases in financial markets, for instance, where without liquidity in the system, for instance, you might have trouble of making markets, and as a result, the system kind of breaks down, right? And so, yeah, in many ways, agent-based modeling is very useful as a thought experiment for when the system's not going to work, just as much as it is for a thought experiment as when the system is going to work. Okay. Saw what we had. So thank you, Daniel. That's a great question. And it looks like Alberta just chimed in with another question about not mentioning the forum in the lectures. Any guidelines on how to use it for the course? So I think some people. Oh, I just froze. That's not good. Heck? No. Okay. Great. Okay. There we go. Back again. Sorry about that. So I think some people have started to explore the forums already. I would highly recommend, and that's a great point. I'll definitely mention them during the lectures for Unit 2. But essentially, my advice would be to post questions there. They're another way to get feedback on. There's already been a great discussion, I think, on tipping points versus phase transitions that's been going on in the forums. And quite frankly, I've been enjoying the conversation so much I haven't felt the need to chime in. The discussion's been going pretty well, even without me being involved. So I think that a lot of people are starting to answer it. So I think that it's a great place to kind of ask some questions of other people. Some of the people taking this course have expertise in different areas, or maybe have applied agent-based models quite a bit. So I highly recommend going there. I try and monitor the forums. I'm not confident I'll get to every answer and every question. And if I see that the questions are taken off, I'll definitely support them as much as possible. So go there whenever you have a question, or if you just have a cool idea, you want to share a life pro tip on NetLogo, right, or agent-based modeling, go and post them there for sure. There are automatic subforums that get generated for each unit. So if your question is specific to a unit, go ahead and post it in that unit. There's also kind of the meet and greet subforum as well, if you want to kind of contact people of like-minded interest, right? And there's the announcements and some of the other forums as well. So highly recommend. Maybe I'll spend some time talking about that during one of the units this week. Great idea for sure. Okay. Okay. Well, it's almost noon here on the East Coast, and so I'm going to start to wrap up. If anyone has any questions, feel free to chime in quickly. Just want to quickly repeat the announcements I made at the beginning of the office hours. What we're working on this week is just wrapping up Unit 1. The test for Unit 1 will go live on Friday. To get your certificate, by the way, if you're continuing on for the full course, you have to get a 70% average across all the tests throughout the course. It doesn't mean if you do poorly on this test, that's fine. You can still do better on the next 8 tests that there are, right? The other thing to mention is that Unit 2 will go live on Monday, and that unit will start to cover Introduction, NetLogo, things like that. Also wanted to mention there have been some questions about the references posted in the forum. Anna Maria is actually working to try and get the references linked to the videos so that those will show up in the future. so that when you take a video, once you watch the video, anything referenced in the video will be listed below the video automatically, so that you can kind of find the references to that I talk about in the lectures. I always try and post at least authors and year on the slides themselves. So if you have any questions about them, you can always shoot me that little reference, and I can probably generate the full reference for you. Also, finally, equivalency with the textbooks came up, and essentially Unit 1 is equivalent to Chapters 0 and 1 in the textbook. Unit 2 will be equivalent to Chapter 2. And then as we go forward, they'll just line up naturally. So Unit 3 will be roughly Chapter 3. If there are any deviations from that, I think that holds at least through 5 or 6. I will definitely let you know as we go forward. It may be a little bit different when we get to the end of the course because I kind of consolidated some of the chapters together a little bit. So, yeah, roughly that's the way to work. Okay, well, I just want to thank the live participants. So thanks to Sebastian, Paula, Alberto, and John, who are all able to join in this week. Thank you very much for your time, and I'll see you guys all next week or sometime in the future. And if you have any questions, let me know. Take care. Bye.
All right. Thank you.
Bye.